Okay, AP Chem, now that we've learned the difference between ionic, polar covalent, and nonpolar covalent, let's separate them a little bit more and figure out what we need to know for the AP exam. So remember, this all has to do with electronegativity. Compounds with the greatest difference in electronegativity will be ionic. Typically, it is greater than a 1.67 difference in electronegativity, but you're typically not going to get an electronegativity scale. So really, most of the time you're going to see this is a metal with a nonmetal. Remember, nonmetals are highly electronegative and metals are low electronegativities. But not all ionic compounds are created equal. They might ask you to compare which one of the ionic compounds has a stronger lattice energy, is what they will call it. Lattice energy is the energy required to separate a mole of an ionic solid into its gaseous ions. It cannot be measured empirically, but it can be calculated. So typically, I'm going to go through and show you this is the NIMSI Math and Science Institute's bonding summary. So remember, ionic compounds have very high melting points, high boiling points. They are solids at room temperature. They dissolve in water to some degree. Some are insoluble, but dissolve a little bit. If you remember back to KSP, some dissolve completely. So at room temperature, they are either solids or dissolved in water. And remember, lattice energy is the energy required to separate a mole of ionic solid into gaseous ions. Now, I'm going to go down here and show you Coulomb's law, which is how we describe lattice energy. So E equals K. This is my constant K. And these are the numerical charges on the ions. And this is the radius, which is the distance between the ion centers in nanometers. So if you notice, energy is going to be measured in joules. Nanometers here will cancel with nanometers there. And Q are the ion charges. So let's go down and see if we can find more on this. So Coulomb's law, it has to do with the positive charge times the negative charge over the radius. Now the radius is going to be super, super, super small. So the first thing we're going to go to is Q's on top. If the charges on the cation and the anion are the same in two compounds, then you have to compare the radius. So let me show you what I'm talking about. If I have LiCl compared to CaCl2, the ion charges are not the same. Therefore, the larger the charge, the greater the lattice energy. So if they asked you to compare these two, you would say, well, +1 times -1 is 1. Here we have +2 times -1 for 2. So because of the fact that these have larger ions, you would say the lattice energy for calcium chloride is greater. So always compare the charge first. If the charges are the same, for example, in this case, they're both 1s, so we can't rely on the charges because the charges are the same. Then we have to compare the ion sizes. So both of the anions are chlorides, so they're the same size. Then we're going to compare lithium to sodium. So remember, as you go down a family, the ionic size increases. So sodium is larger. So that means that sodium will have a larger denominator. Remember, when the denominator is larger, it makes the number smaller. So when you're comparing these two, you would say the smaller the ions, the greater the lattice energy. So when you're using Coulomb's law, that's when you're trying to tell me which one of these ionic solids will have a larger lattice energy. Let me show you what lattice energy is again. So this one's lithium fluoride. Generally, lithium fluoride will be lithium solid. That's how he occurs at a standard state. He is a metal, and all metals are solids at their standard state, except for mercury, which is a liquid. And then fluorine is a diatomic element, and it occurs as a gas, like such. But I only need one fluoride, so I need half of a mole of fluorine, and then pack them together to be lithium fluoride. So this is how it occurs in nature. But remember, the definition is to take gaseous ions and pack them into a rigid crystal lattice. So this right here is my lattice energy. So this is kind of like a Hess's law type of deal, because we're going to start here. So the first thing I would want to do is take lithium solid. I need to get lithium solid into being a gaseous ion. That takes more than one step. So the first thing I'm going to do is I'm going to take lithium solid and I'm going to turn it into a gas. Taking a solid and turning it into the gas is called the enthalpy of sublimation. So the enthalpy of sublimation for lithium is 161 kilojoules. So I'm going to have to add 161 kilojoules to lithium to get it to be a gas. Now I need for lithium to lose its one valence electron. To lose its one valence electron is the amount of energy to pull that electron off. That's called ionization energy. So the amount of energy to turn lithium into a solid is the first ionization energy, because I only need to rip off one electron here. So it will take 520 kilojoules of energy to pull that electron off. Now let's go to fluorine. So fluorine occurs as a gas already, so I don't need to sublimate it. But what I need to do is I need to break the bond that is the fluorine-fluorine bond. So the amount of energy to get it from being F2 to just F is going to be the bond energy. The bond energy for fluorine, but I don't need a whole fluorine, so I need 1/2 of this bond energy because of this 1/2 here. That's going to take F2 gas, split it up into F. And then the next thing I need to do is I need to give fluorine an electron. Notice this. So this is called the electron affinity. It's the amount of energy associated with forming an ion F- from an A. Notice in this case, this is an exothermic process. So in this case, energy is actually released. So here's the things that I need to add. 161 for the enthalpy of sublimation, 560, which is the first ionization energy for lithium, 77, which is half of the bond energy for fluorine, and then I get back 328 kilojoules, which is the electron affinity for fluorine gas to become a fluoride gas ion. And then once I have them exactly where I want them, the lattice energy is going to be the amount of energy that is associated with packing it into a rigid crystal lattice. So now you would need to take some time and practice deciding which one would have a greater lattice energy based on the charges on the ion or the radius. And also recognize the steps that add up to lattice energy. So here's all the different pieces and parts. Think of it as like a Hess's law problem, and you can quantify the process that it takes to pack ions into a rigid crystal lattice.